Now that we've laid the network foundations and how communication happens, let me be the first to welcome you to the world of Ethernet. We're going to start building up in that OSI model, starting at, we've seen a lot of the physical standards, but moving into the data link standards with Ethernet technology. We're going to look at the evolution of Ethernet, where Ethernet came from and where it is today. We'll look at CSMACD, which is really the rules Ethernet devices have to comply to when they're speaking on a network. We'll then look at how they can speak, three different types of messages that a device can send in a network and how the network handles them. And then finally, we'll come to the official explanation of a MAC address. We've seen them a couple times, and now we'll get to break them apart and define what they are. Let's start off by talking a little bit about the history of this fabric of networks that we know as Ethernet. 1973, Xerox, the same people who created that photocopier that's probably sitting in your office, created the Ethernet standard, and its original speed was 3 megabits per second. 1982, they decided to standardize it between vendors to where everybody would use the same Ethernet standards and people would create network cards that all complied to this. And this was a big step because before this, networks were pretty much proprietary, meaning you purchased this certain type of equipment and only that same vendor would be able to communicate on a network with its same pieces of equipment. Now, 1995, big leap, 13 years later, fast Ethernet emerges, which will remain the standard for Ethernet and our Ethernet connectivity as a popular standard until fairly recently. 1995 was a big year because 100 megabits per second is more than enough speed to carry even the applications that we run today. We'll talk more about speed in just a moment. 2000 was where gigabit Ethernet emerges, 1,000 megabits per second. That's where the gigabit term comes from. Now, it's kind of ironic because they did some studies of high technology companies and how much bandwidth people were using on their network connections, and they found out that these high technology companies, and when I say that I mean technology or companies that deal in technologies, they work in technologies, companies like CBT Nuggets or Cisco, these people who really technology is their game. And they did a study on how much bandwidth was used, and it was 5% of 100 megabits per second. The average user, on average, throughout a day, uses 5% of the 100 megabit per second link that they have to their desktop. So you might be wondering, well, why are we upgrading to 1,000 megabits per second if we're not even using 5% of fast Ethernet? Well, gigabit Ethernet typically comes in on your links between switches or your links to servers and things like that that really eat up a lot of bandwidth. Again, we'll talk more about the speed in just a moment. 2002 was where the 10 gigabit Ethernet emerged. It's kind of funny. You see these dates moving closer and closer together as the technology curve kind of keeps increasing. And that's 10,000 megabits per second. And then finally, in 2007, we saw 100 gigabit Ethernet standards beginning to emerge. Now that we've talked about the speed and the history of Ethernet, it brought to my mind a thought that I want to make sure everybody's on the same page with understanding the speed and size concepts in networks, because most of what we deal with nowadays in our PC realm is things in terms of bytes. Now, when you think of a byte, when you're thinking of a PC and how much size a byte consumes, you can think of that as one character. It's like if let me finish writing. One character. So if you open Microsoft Word or Notepad and hit the E key on the keyboard, E, you are staring at 1 byte of information. F, I now have EF, 2 bytes of information. It's just one character. Now, if you go larger in size, you actually will move up to a kilobyte. And that's where you have 1,024 characters. Would have been nice if they would have rounded it to 1,000, but it's 1,024 characters. Think of 1 kilobyte as a page of information without any margins. It's about 1,024 characters, or a kilobyte. Now, going beyond that, we get into sizes that most people, even non-technology people, are familiar with. This is where you get into your megabyte, where Most people think of that as their RAM sizes or memory sizes within their PC. And that's 1024 kilobytes. And the same scheme keeps up the whole way down, 1024, 1024. This goes down into a gigabyte. Now we're into hard drive space. Most people think of hard drive space in terms of gigabytes. Then you move beyond that and you get into terabytes and exabytes and petabytes and blah, blah, blah. You go down the whole scheme. All I know, there's quite a few in between, but I know the last two in this list are yottabyte and zettabyte. They remind me of Star Wars characters for some reason. But that's how big we've defined our sizes. But when we're talking about networks, we don't talk in terms of bytes and all this size on the computer. We talk one level smaller than what we deal with day to day, and that is a bit. Now the bit goofs everything up because we had this beautiful scheme of 1024, 1024. But how many bits are in a byte? Many of you may know that one. 8. There are 8 bits inside of a byte. And what is a bit? It's the most fundamental computer or technology thing that you can deal with. I don't even know how to describe it. It's just a 0 or a 1. It's an on or an off. It used to be in the old days, 30 years ago or so, people would write programs, maybe you did back in college, where you would use punch cards and punch out these little chads from the cards and feed them into the PCs. And those punches represents on and off, those zeros and ones. And as far as we've evolved in all of our computer terms and days, we still work in terms of bits, meaning you see on the screen an E inside, but really to make up that E, the computer goes 0, 0, 1, 0, 1. I don't know what the exact representation of E is, but there's 8 ones and zeros that the computer sees when you hit that E on your keyboard. It's the same thing with numbers. If I were to say the number 5, the computer would say 0, 0, 0, 0, 0. I'm trying to think what exactly it is. 1, 0, 1. That's how it sees the number 5. And we'll get into that skill, converting decimal to binary or bytes to bits later on. It's essential for subnetting. But when we look at speed on networks, everything is rated in bits per second. Meaning, just on that previous slide, I said the Ethernet standard started at 3 megabits per second. Notice the little b. I can very rarely write in lowercase, but that's one that I always do. 3 megabits per second because it's rated in terms of ones and zeros. I've heard a lot of people confuse this and say, oh yes, my network goes, say, 3 megabytes per second. Actually, I love it. My dad is one of those technology guys who knows just enough to be dangerous. And he gave me a call on the phone a couple weeks back, and he said, "Jer, you'll never believe this. Cox, who's our service provider, they're our cable modem service provider out here. He said Cox just upgraded my link to 8 megabytes per second." And I go, "No way, no way!" I'm freaking out, and usually when I do that, he knows he said something wrong, and he goes, "What? What did I say?" I said 8 megabytes per second would be an insane amount of speed. If you think about it, how would you figure out if somebody told you 8 megabytes per second, how many megabits would that be? Well, you'd have to multiply by 8 because there's 8 bits in a byte. So 8 megabytes per second is actually 64 megabits per second, which would be a killer cable modem connection to have. But nobody that I know of is giving a speed like that for $40 a month. So you get to get used to, when you're thinking about networks, working in terms of megabits per second or kilobits per second or even gigabits per second. Everything's in bits. Now, when you're lining Ethernet up to the OSI model, Ethernet consumes or matches up to the bottom 2 layers. It is both a data link and a physical standard. At the data link, it's been divided into 2 sublayers. I know, the OSI model was bad enough, right? We had to add more layers. Well, it's not too bad in the sense that the 2 sublayers are very logical. Meaning you have the MAC layer, which we've already seen what kind of addresses? MAC addresses. That's the layer that defines the addressing that Ethernet uses and defines the standards that every computer has to have a MAC address that ties into an Ethernet network. Now above that, you see the logical link control layer, LLC. All that does is pick what direction it's going to go into the network layer. Now remember, network layer is the one that houses typically IP addresses. That's the logical addresses that we assign our computers. Now, IP addresses are just one type of address that you could have at the network layer. You can also have an IPX SPX address. That's another protocol that you could use. You could have an Apple Talk address. There's many different network layer protocols. I know all we think about today is TCP/IP, but if you are using some of those other protocols, you have to have a logical link from the data link layer up to the network layer. And all this field really is a field that tells the PC or device as it's passing this up the OSI model, going through the de-encapsulation process, which network layer protocols should get it. Most of the time it'll be IP, but it could be some of those other protocols. Now down at the physical layer, Ethernet also defines many physical standards, and that's where you see your things like Cat5 Ethernet cable or wireless standards or fiber optic standards that come into play. I mean, think about it like data link layer is your wheels on a car, right? You're driving around. It doesn't really matter what road you can drive on as long as it's a road that's designed for tires, meaning you're not going to be able to just start driving across the water or something like that because there are some physical standards that just can't carry Ethernet, but for the most part, Ethernet can drive over nearly every type of cable that's out there. Have you ever been to a meeting where you're just sitting around a conference table and everybody's kind of, talking about what's going on at the company? You ever notice how there's some unsaid rules at these meetings? Like if the CEO or the authority of the meeting begins talking, everybody has to stop talking because that is the authority. Or you just don't interrupt people because it's just not polite, or you shouldn't anyway. If they're talking at the meeting table, you don't just jump in the middle of the sentence and say, well, I've got a thought, and kind of curb the conversation. It's kind of the unsaid rules of the meeting table. And in Ethernet, we have these rules governing how you talk on an Ethernet network, except they're a little more stated than the meeting room table is. The rules are known as CSMACD. And when I say rules, it's really a standard. Every Ethernet device that's designed, a network card, a switch, everything that works in this Ethernet world has to comply to these rules. CSMA-CD means Carrier Sense Multiple Access Collision Detection. I broke it apart to define what each word or set of words in that definition means. The carrier represents the network signal, meaning there's going to be network signal sent on Ethernet. Sense is the ability of all the PCs connected to the same Ethernet network to detect if there is a carrier signal at the time. For example, if you're in a meeting room, you should be able to detect if somebody is talking and not interrupt them. In the same way, the Ethernet device should be able to detect if somebody's already talking on the Ethernet line. Multiple access means all devices have equal access. Everybody that's plugged into an Ethernet network is considered equal. They just have to wait until each other stops talking. There's no priority is what that's trying to say. Collision detection defines collision, what happens if two devices send at once, meaning they both were trying to sense, they were both trying to detect if there was a signal, and they didn't hear anything, so they assumed it was safe to send, and when they both sent, they collided. Detection, that is how the computers handle the collision when it happens, because they will be able to detect that they collided, and they'll have to resend the data. Talk about how that all happens in just a moment. Now, you may have heard, and I think I mentioned earlier in this series, the competing Ethernet to the competing standard, I should say, to Ethernet was actually token ring. You may have heard of token ring before. Token ring used CSMA/CA, collision avoidance, meaning in a token ring network, there was never a collision because literally there was this token. You had this, that's where the ring came in. You had all these computers plugged into a ring, and there was this token that flew around the ring. It's kind of like, think of it like an arcade token flying to each PC at the speed of light. And whoever had the token at the time would be the person that would send. So for instance, if this PC grabbed the token, it would attach its data and it would fly around the ring to this PC and drop it off, who had some data, and would fly around the ring to whatever device it was sending to, and just be picking up data as it goes. So since there was only one token, only one person can send at a time, meaning if you didn't have the token, you can't send. Collision avoidance. The problem with collision avoidance is they found the token could only go so fast, and they reached a maximum speed. I think it was somewhere around 33 megabits per second. That once they reached that, they couldn't really go much faster with collision avoidance, so they chose to go with collision detection instead. Moving along with those rules of communication, there are three different types of communication that we can have in our Ethernet networks. The first kind is considered a unicast message. This is when one computer wants to send to another, thus the term uni, one-to-one communication. So if this computer over on the left, 172.16.1.11, let me just fix my drawing tool here. This guy over here wants to send to just this guy. With the switch, you can have a message come in, not bother anybody else, and come right up here to this PC. That is considered unicast communication. The broadcast message, on the other hand, is the exact opposite of the unicast, meaning it's going to be one message to all. So if 172.16.1.11 sends a message into this switch down here, and it's a broadcast, like an ARP packet that we talked about before, that will go out every single switch port except for the one that it was received on. The switch is smart enough to say, well, if he's sending a message to everybody, obviously he does not need the message, so I won't send it back out that port. But it will go out every single switch port. All PCs will receive that. And for example, if this is an ARP message, then only the one that it was destined to would respond. The other two would end up dropping it. The last type of communication is considered multicast, and this is one of the newer forms that a lot of people are starting to use nowadays. Multicast is one message to a group. So instead of it going to everybody like a broadcast, a multicast message comes in and maybe just goes to these two computers down here if they are a member of the multicast group. The advantage of multicast is that it helps with the bandwidth, meaning you only have to send one message to a group. Well, let me expand on that a little bit. If I had unicast messages, let's talk about like a streaming radio station. You can actually listen to the radio on the internet or on a LAN. If I have a server that's sending out unicast messaging, then one person joins the radio stream and it starts a signal that way. Another person joins the radio stream and it starts a completely separate signal that way. And another person joins in and you get a separate signal that way. And what you're doing is you're increasing the server load, because it's having to maintain 3 or 4 or 5, however many PCs join, separate streams all at the same time. And you're eating up a lot of bandwidth, meaning you have to have one unique stream for each PC. Now, the problem with going to a broadcast model is it would only have to send one stream out, but everybody would get it. It would be a network flood, and everybody would have to drop it that's not tuned into the stream. So that would cause a lot of extra network traffic for maybe just 2 computers or 3 computers that are listening, and everybody has to get it. So that's where multicast comes in. Multicast allows you to send one message to a group of people to where it's just one stream being sent out, and only the people that want that stream tune into it. Pretty cool communication type. The last thing that we'll talk about in this opening video to Ethernet is the MAC address. We've seen them quite a number of times at this point, but we haven't officially described where they come from or why they're 12 characters or what those 12 characters really mean. Well, honestly, I don't know why they're 12 characters. Whoever created the MAC address standard, I'm sure, just said that will be how long they are. They're hexadecimal, which means 0 through 9, and A through F are valid characters. Now, every single MAC address is essentially divided in half. meaning the first 24 bits, or the first half of that MAC address, first 6 characters, are considered the organizational unique identifier. When an organization or a company goes into manufacturing Ethernet devices or things that participate in Ethernet networks, then they need to register to get a valid range of MAC addresses that they can use. They are assigned specifically to that organization. For example, you might have an organization, just as my example here shows, get the identifier 0019D1. From there on out, that company has to use MAC addresses from that range. And you can see the second half of it is considered vendor assigned. The second set of 6 characters are up to the vendor to come up with. So they just create MAC addresses on the fly of what they want their network cards to be identified, but every MAC address must be unique. Now, these organizational identifiers are well known. I mean, you can actually look them up. I went to a website. Actually, I just did Google search for MAC address lookup, and this is where you can plug in your MAC address. Matter of fact, let's try it out. I'll open a command prompt and type in ipconfig. Now, on my computer, I have all kinds of network cards, that most of which I don't use. But if I scroll back up to the top, oh, sorry, I need to type in ipconfig/all to get the MAC address. Let me scroll back up to the top where my real network card is. That would be this guy right here. Now, I guess it's kind of anticlimactic because it shows description, Intel, gigabit platform. So I know right there that Intel is my manufacturer, but let's see if the website can figure it out. I'm going to highlight, and on command prompt, you can right click to copy to your clipboard. And I'll just say paste that right in there. And I'll hit string, and it says search results, and right up there, notice it looked at the first 6 characters and said, oh, the vendor of that is the Intel Corporation. So at some point, Intel had to come to the powers that be, we can call them they for now, and said, I need to create some MAC addresses, here's some money. They said, well, here's your organizational identifier, and now Intel is creating network cards using their vendor assigned bits. That should be a good view of the foundation of Ethernet technology, just showing where it came from and how it communicates. So we talked about the evolution of Ethernet. 1973, Xerox began the evolution, and it's progressed ever since into some speeds that I'm sure people didn't even dream of back in that day. Then we talked about the essence of Ethernet technology, CSMACD, which is the rules of communication. Essentially, it senses a signal, it listens. If nobody is sending, then the Ethernet card is allowed to send. Methods of communicating in the LAN, we talked about 3 of them: unicast, broadcast, and multicast. 3 different ways you can send messages. And then finally, we saw the official explanation of the MAC addresses. It is split into 2 pieces. Half represents the vendor, half represents the unique ID from that vendor. I hope this has been informative for you, and I'd like to thank you for viewing.